Ladies and gentlemen, please welcome Senior Vice President, Security Products, VMware, Tom Korn.
Terrific. Thank you so much. I've had an opportunity to do quite a number of presentations here at VMworlds or at RSA conferences. I've never been excited about a session like I am about this. This session is going to be a high-wire act. We have an opportunity in this session to not just talk a little bit about how we see some of the fundamental issues facing security, and also about what our vision is and where we're trying to focus our efforts and our strategy and where we are in terms of building that. We also have an opportunity in this session to talk in a bit more depth about where we're going. And not just talk about it, show it. And this is the high-wire act. In the second half of this talk, we actually have set up in a data center in Palo Alto a live multi-tiered banking application that is currently running. And we're going to hack into it. We're going to hack into it in a variety of different ways. And we're going to give you a preview of a bunch of new technologies that we're working on and applying it to that. So it's a high wire. It's live. It's completely live. But I think you'll find it very, very insightful about the kinds of things that are suddenly possible in a world where the laws of physics are very different in a virtual world. So with that, and frankly, before we dive into all of those details, of course, I'd love to welcome you here to Las Vegas. This is actually the first time, certainly in my experience with VMware, where we've had the VMworld here in Vegas. Vegas has obviously been around for a while. From its early days, in the turn of the century, when it was a small village of about 600 people, to the 30s with big government projects like the Hoover Dam, which are an extraordinary thing to see, where suddenly we have tourists coming here, to the 50s and the heyday, in the early days of the casinos, where suddenly not only was the population growing, but the tourist population was growing, and we had at that point about 8 million visitors annually, to the 90s, where we had the mega resort area. Already population growth was growing quite substantially. The city's boundaries were growing. Of course, up into the 2000s, where not only did we have spikes in population and in tourists, we also were facing the recession. To today, where Vegas is among the fastest growing cities across the country. And, it may have started, like most cities, with some kind of plan, with some kind of structure, but over that kind of growth in that period of time, things outpaced initial plans. Things outpaced its structure, its architecture. And as a result, like many cities, you face all kinds of issues: water shortages, overpopulation, housing costs, traffic congestion. And many of these problems are very difficult to solve. Why? Because they're structural in nature. You can't just simply add a road or add a stop sign or pipe in little bits of water in certain places. It's structural. It's very difficult to rethink it. And how close the challenges of a big city are to the challenges that we face inside a modern data center, which has also grown by leaps and bounds and has also outpaced whatever structure or architecture perhaps were initially had in mind as when we put it together. A data center in many ways is like a big city, where the roads are networks and the buildings are servers. Now, there was a time inside that city where our applications were like monolithic stacks, right? Think of a skyscraper where every floor of the building represented different functions of that application, from storage to databases, application logic, user interfaces. In that world, you could secure that by placing guards at the front of that building, and you could be assured of two things, two properties. One, there was nothing that was going to get in and touch any element of that application without passing through that inspection point. And two, those guards only had to focus on that single application, on that single tenant of that building. And so the kinds of policies and inspections that had to look for could be very granular and very simple at the same time. But that's not what an application looks like today. An application now is a distributed service. It's web servers talking to app servers, talking to talking to databases, storage servers. It's composed services. An application today is a distributed system. It's a network. And we have hundreds, sometimes thousands, of these kinds of applications commingled on a common generic infrastructure. Right? And it's that very issue that has driven largely flat network architectures in order to accommodate that kind of organic growth with these kinds of commingling of composed services and distributed systems. When we go to protect this, to secure this, right, our policies, ultimately, we're not trying to protect servers or networks. We're trying to protect applications and data. But our application itself is actually not a single entity. It's little pieces of buildings all across that city. Our policies are about users and applications and data. But we don't have those handles inside that city, right? We have handles for things like our perimeter. That's a very tangible thing. I can place things on egress points. Or I can group and segment assets of similar types, web servers in one segment, app servers in another segment, application gateways, back-end services. And to be clear, there are logical security policies that can govern this world. Web servers probably shouldn't talk directly to storage servers. App servers should probably only talk to database servers over certain ports and protocols. But make no mistake, this is all, at some level, security theater. Because it doesn't really stop issues like lateral movement, and it doesn't stop issues like the complexity of policy when you move the control from the perimeter inside. To give you an example of why, the key thing is that we've commingled in any one of these segments components from many different applications, right? So think of the myriad of ways that an attack can circumvent our perimeter and come inside, from users, from laptops, etc. If it compromises any single point, any single application inside any one of these segments, it has freedom of movement inside that segment. And then it can simply use the distributed applications themselves to cross over those segment boundaries. Lateral movement goes unabated, and frankly, so noisy that it's difficult to find the needle in the haystack. But that's not the only problem in this architecture. The other problem is policy complexity, because it turns out to be orders of magnitude more complex to put a control that was once on the perimeter inside. And here are two examples of why. First of all, where would you put them? Right? I had a single egress point. Now that I'm putting things inside, it's a city. You're going to put one on every street corner? Then you run into all these issues like commingled policy. That firewall up there, sitting in between two segments, has to have the policies for every conceivable application that might cross its way. That's why it has 30,000 rules in it. And when was the last time any of you removed a rule from a firewall? Right? It's an incredibly complex thing. Right? And then you have things like commingled policy. I have multiple instances of controls, so that if traffic flows from one machine to another and hits 5 different firewalls, our effective policy is the policy of every firewall that you hit in the order that you hit, depending on the route that you took. It becomes intractably complicated. Now, it is, in essence, in our view, an architectural issue, an architectural gap between what you're trying to protect, the applications, and where you're trying to protect it from, the infrastructure. From the policies that we're ultimately trying to enforce to where the controls are going. The infrastructure has no longer a good proxy for the applications sitting above it. And that is an architectural gap that is at the center of so much of this problem that we're facing around security. Now, one way of addressing this architectural gap is to build a different data center for every application. If you do that, you actually could address some of these issues, right? You could, a single data center application, or an application having its own data center, would be very difficult to do lateral movement across from data center to data center. Furthermore, it's very simple to align controls. We're essentially going back to our skyscraper. It would roughly cost the gross domestic product of a small European nation to do this. But other than that, conceptually, makes sense. Now, what on earth does any of this have to do with virtualization? And here's the kicker. Right? Virtualization, if you think about it, is an abstraction layer sitting in between the infrastructure below and the application sitting on top of it. And the really interesting property of that is the ability to, in an overlay, abstract the application onto a different plane and to be able to operate controls on that plane. Right? And it gives us three very interesting properties. Alignment, the ability to align controls in the infrastructure to the application above it. Ubiquity. This has become a pretty ubiquitous infrastructure, right? It covers large percentages of our compute base, now our network-based storage, and isolation, right? It provides a place to put security and software that doesn't necessarily sit in the same trust domain as the endpoint and the attacker. And that's a very important property, to be able to do things from a point of integrity. So, how does this work? Many of you are familiar with network virtualization, but for those of you who aren't, a 15-second primer on it would be, you're all familiar with server virtualization. Every one of those hypervisors that you're using has virtual switches. In essence, an oversimplified view of this is that in network virtualization, we're taking control of all those virtual switches, because no virtual machine can talk to any other machine, virtual or physical, without passing through one of those virtual switches. So that if you take control and create a series of other richer abstracts around it, you can essentially create a network hypervisor. And out of that, you can essentially describe and create a control plane for applications. In essence, creating a little mini data center around an application. In many ways, this is what is at the center of this notion of micro-segmentation, the ability to create a virtual data center around an application. So instead of building a physical data center for our applications, we can build a virtual one without changing our physical network, because we rarely have the opportunity to re-architect our city. We have to have solutions that can build an overlay on top of that. This could have profound impact on security, on all elements of security. I mean, think of prevention today. Prevention today is largely about real-time detection and inline filtering. And it's highly challenged, trying to keep up with the constant pace of threats, the evolving nature of those threats. It's very difficult to analyze increasing amounts of it in deterministic ways. It's very difficult to understand threats from a single point or react to it. And it's very difficult to do it from a point of presence that is in the same trust domain as the attacker. It, as a result, has not yielded as much benefit as we all would have hoped. But in this world, the thing that we could add to that is the notion of least privilege. This is one of the oldest principles in computer science, dating back to the early 70s at MIT. Very simple concept. It's basically need to know. Right? And an application should have access to the resources that it needs to get its job done and nothing more. But until this point, been very difficult to do in highly dynamic environments. It also can have an impact on detection. Now, there's a host of, we're not necessarily doing analytics on our end, but what we can show is context, and context is everything. It's more than context. It's being able to align things. There's a big difference when you're looking at a series of pieces of data and they're not aligned, and you're trying to make sense of it, as opposed to something that can help you align the telemetry points around a unifying principle. And in this case, the ability to say, I can see my alerts, my data, my telemetry in the context of the application that's sitting above it. My network controls can see endpoint telemetry. My endpoint controls can see network telemetry. And lastly, it's about response. Today, response is largely manual, unorchestrated, and as a result, it's labor-intensive, it's inefficient, and it sometimes creates as many problems as it solves as we try in the middle of an attack to try to pull the systems or address the campaign as a campaign as opposed to playing whack-a-mole in our environments. But in a virtual environment, the promise is to be able to automate some of the remediation and leverage the infrastructure itself as a remediation mechanism, right? So, this helps tremendously in the context, you think of a context of a modern attack, a modern kill chain, right? This kill chain, which really represents the process of an attack, the majority of our resources today are still going into trying to prevent intrusion. And where a lot of the things I'm discussing here today helps us tremendously in addressing propagation and extraction. That stage in this attack where someone has managed to get in somewhere, maybe not in a critical resource, but is escalating privileges and moving laterally through the environment, ultimately working their way into critical applications and breaking in either through exploits through network connectivity or data level, compute level exploits from the top down, or from infrastructure and data level exploits from the bottom up. It's in these areas, in that middle part, where we can make huge strides forward. And it's critical because security is an asymmetric battle. An attacker fires 1,000 bullets and we have to stop all 1,000. They only have to succeed once. But it gets more symmetric as you move through these kill chains if we have the ability to see things in context and react and address and lower our attack surface. Our vision here is a simple one. We have to move from trying to secure infrastructure in data centers to focusing on really what we're trying to protect, the application. Think of a security scope, not as a data center, but as an application, a regulatory scope, a composed service, and to be able to create least privilege around that at a network connectivity, at a compute, and at a data level. And then to be able to align our security controls around these concepts. I'm not generically sticking a network control on a network link. I'm aligning it to the boundary of an application. Now, that's all conceptual, and we'll go into a bit more detail on that. Let's start with the network piece. And this is what's here and now. This is what this is what's driving a lot of the sales of NSX today, right? Instead of having a traditional segmentation, which you still can have, it's the ability to focus on a critical application, a high-risk scope, and to be able to, in an overlay, bring that up and then create a micro-segment around that. Now that does two things for us. It addresses the lateral movement issue because compromise of a system outside this, even in a commingled segment, doesn't have access into this. So it helps us address a lateral movement issue. It also provides a means of aligning our security controls ultimately to what they're protecting. And make no mistake, misconfigurations and misalignments are as big or bigger, the biggest part of hurting us in security. This is what's driving today a huge percentage of NSX and network virtualization sales. There's a variety of use cases that people use this for, right? Automation, disaster recovery, security. Security is perhaps the single biggest use case driving it today, and it's really become it's really one of our fastest growing areas in the company. It's really around this. This is what's shipping now. All right. Let me transition for a moment to compute least privilege. And a compute least privilege, this doesn't exist yet today. And this is more direction, and this is where we're going to start to get into technology preview. How do we address that? Now, here's the challenge on the endpoint. All of the virtual machines and what I just described in this microsegment consists, of course, of operating systems, OS, and a series of security agents. The challenge that we face on these is many. Finding malicious activity and malicious software on an endpoint is, in every way, like finding a needle in a haystack. It's hard. It's hard because it's constantly changing, the malware. It's hard because it's systemic. It's hard to sometimes analyze things from a single point. And it's hard because it lacks isolation. It's very difficult to do security from an environment that's the same trust domain as the attacker. Now, the concept here that we started to work with is, can we apply the same concept that we just done with NSX to the compute stack? Can we, in essence, create a least privilege model, right? We don't need all that hay for this application. We need a small percentage of it that's critical. As a result, it's a much smaller attack surface. And look, there are no silver bullets in security, but it creates a much brighter signal if things do get by that. And that's the concept here. All right. How does that work? To dive a little deeper into this, essentially what we started playing with is the notion of creating an attestation service over the compute stack that's sitting above it. to be able to monitor the operating system kernel, the processes running on top of it, the way those processes were communicating in and out, and to be able to look at that against a manifest of what was the intended state of that virtual machine. Well, how do we understand the intended state? And the way we've been playing around with that is to be able to pull context from automation systems, provisioning systems like VRA, like Puppet, like Jenkins, and to be able to parse down from there what was the intended state, the birth certificate, if you will, of this virtual machine. This virtual machine was intended to be a Windows 10 machine running Django with some Python processes communicating over this port. It was part of the web tier of this application, right? Then that can feed and create a manifest that is then being attested to in real time at load and runtime. And then the policy becomes, well, if this deviates from its manifest, what do we want to do? And there's a whole variety of things that we have at our fingertips using NSX and ESX. We can bring up gold images, we can quarantine, we can insert full packet capture, we can increase logging, we can harden. The sky is the limit, right? What is also very interesting here is where we're doing this. In essence, the idea is to put this inside not the guest, but a virtual enclave in the hypervisor kernel. It's giving this isolated trust domain, this secure execution zone that has privileged visibility into the guest. It has the ability to do this from a trusted environment, right? Very different from anything that exists today in the endpoint security world. This is the idea behind this. The other piece is that we open this up to the partner community so that your favorite endpoint security products have the ability to leverage the same context, the manifest. They can be protected by this attestation, and they too can leverage the virtual environment as a remediation backbone. All right? So that's the general idea. Chris, come on board, and we're going to introduce. This is Chris Cord. Chris works as part of my team, and we're in the process of building some of these things. And what I'm going to show you is one of the things that Chris and team are working on. All right. Here's what we're going to do. This is all theoretical at this point. We're going to break into a bank. Okay? And this is the high wire rack because we're doing this live. What we've done is we've set up a multi-tiered application in our data center in Palo Alto. We are hardwired connected into the internet. We're VPN'd in, okay? So essentially here, we have a Django app server, or a series of Django app servers connect to a series of SQL Server databases, and we've set up a mortgage application. And what we're going to do is we're going to break into that mortgage application, and we're going to get rid of my mortgage. If any of you would like your mortgages taken care of, please see us after the show. And we already have hands. Okay. And then we're going to start to play with some of these concepts and actually see some of a tech preview of some of the technologies and how it would apply to this. So do you need a few seconds to keep going, and I'll sort of do a bit of the setup?
Second, yep.
Okay.
Give me 1 second.
Okay, so here's the idea, just so that you see what we're going to do is we're going to do an exploit to set up a reverse TCP connection to that Django server. This is about coming sort of top-down into it, okay? So we've set up standard Django configurations, etc. We're exploiting some vulnerabilities in that. We're setting up a remote listener. We set up a remote TCP connection, right? So the communication is going outbound, right? We've written a PowerShell script. We've also done an attack with a Python script, which we load in that gets us into that Django server. And then once we're in that, we have free reign in there. So we can see things like the configuration of that and what are the credentials that it's using to connect to that database. We then essentially add that to our Python script, or actually we're going to start with a PowerShell script. We're going to start with a PowerShell script to use that credentials and the visibility it has to the SQL Server to go in and zero out that my mortgage. Okay? That's the general idea. Right? That's where we're going to start. Once we get through that, we're going to do a couple of other attacks to this. We're also going to do an attack where we do a SQL injection attack on that Django app server. So instead of running some scripts in it, we're actually taking control of that, and we're going to use that to zero it out. Make sense? Okay? Sounds like fun? How you doing?
Good.
All right. So Chris, let's start by logging in, and we'll get into we'll take a look at my mortgage.
Okay.
Oh, yes, sorry. Could we bring... Okay, so now we're looking up to our login. Here we go. $10 million, your basic teardown at Palo Alto today. So, all right, here we're going to do, we have a mortgage, we're going to flip over, and Chris is going to start by setting up a remote listening, right? So Chris, walk us what you're doing here.
So as you said, we're basically going to leverage port 80, which is an open port on the application server in order for our app to run. And we're going to issue a command injection attack into the application server for it to make a remote connection or reverse TCP connection back to our Kali box. So I'm just using Metasploit here. I'm just going to set it up.
Okay, so while you're doing that, we're setting up the
Started
remote
on port
listener.
80. I'm going to tell it the host of our machine.
All right, now you're pulling the IP address, right?
So once I give it the host, and then I'll start the exploit. So this is basically starting the reverse TCP listener on our Kali box.
Okay.
And then what I'm going to do is I'm going to take the payload, the actual malicious payload. So this is just a command injection payload that we generated via SE Toolkit, which is another tool that comes in with Kali Linux. And I'm going to issue that to our application server. So we'll just come back to our app server. So I submitted that malicious payload, and what we should see is the app making a reverse TCP connection back to our application, or our Kali box.
All right.
So there you go. So now we have a reverse TCP connection initiated, and essentially what we have now is full console access to that app server.
Got it. All right. So, by the way, we're going to have to speed up. I just realized because we're running low on time. So, all right. So now that we have the remote, we're going to take a look what we see on that box. We have full access, so we can take a look at the config file for Django, right? And that'll tell us a bunch of information about the settings, like credentials, other types of things that we're going to need to be able to connect.
Yeah. So the most important thing here are the database credentials that we're using. So, and as Tom said, we just pre-wrote a PowerShell script that is on our Kali box. And I just did that to save time, but essentially this has all the preset credentials from our database system that we just, achieved through the settings file. So what I'm going to do is I'm going to take that and I'm going to upload that.
So he's now going from the remote box where the script is mating, he's uploading that to a hidden folder inside the Django server, and then he's going to have the Django server execute it. When it does that, the Django server is going to communicate to the database and get rid of my mortgage.
So I've uploaded the malicious script, so I'm just going to tell PowerShell to run. I'm going to tell it to bypass any executive protection, and I'm going to give it the location of our script. So now our malicious payload is running, and what we see here is that we have successfully cleared out Tom's mortgage. And then we can come back to our app and log in. If I can type.
This is the best part of the demo. If we just stopped here. All right, great. So we zeroed it out. Now, let's look at the concept here. By the way, we've done this attack in a variety of ways. In the interest of time, but we've run it with Python scripts, a bunch of different ways, all right? Let's look at what the concept of least privilege on a compute stack would mean here, okay? So let's reset the mortgage, all right?
I'm just going to jump into the database system and reset the mortgage, just so that when we run the attack again, it'll work.
All right, so we're going to reset it, and now we're going to set up. Again, the concept here is simple. It's about saying, look, the application team doesn't have to be an expert at security. They have to be an expert at their application. And as they're provisioning their application, essentially we're pulling that kind of information to essentially create a manifest so that we can have very simple security policies for critical applications that say, listen, I need to watch this against the manifest. If it starts to deviate, what is the policy that should be in place? What do I need to do or recommend that the SOC team does? All right, so what you're looking at right now is a security management console for this, right? This is our running tech preview of something that we're building. So,
right, so as Tom mentioned, everything here is built around the concept of a security scope. And essentially what a security scope is, it's is all of the application context that we need in order to enforce least privilege on the compute side around all of the assets that make up that working system. So in the case of virtual machines, it would be all the virtual machines that you need to build out an application. You can put containers in the same concept of a security scope. And essentially, once we have that understanding of what the scope is and how it should behave, we can place very fine and granular rules from a security perspective on top of that scope.
Right.
So in this case, I'm going to dive into our mortgage application scope. This is the app that we were just breaking into. And what you're seeing here in this diagram is not a runtime view of the system. So it's important to note that this is not looking at it NetFlow in real time to generate this view. This view is generated from the provision time systems. In this case, we generated it from VRA to give you an intended state view of the system, right? So we want to be able to look at what the app developers, the infrastructure admins initially wanted to create in order for us to be able to apply security rules on top of that intended state.
Right.
So I'm just going to dive into the app server manifest. And what you see here is this is the specifics that make up kind of the detail of what a virtual machine would have in terms of its birth certificate. So in this case, we have a lot of manifest information at the top here. That's really what allows us to kind of group this into overall security scope. We see that it's part of our mortgage scope. And on the bottom, we have more granular sets of intended state, which is around the allowed services. In this case, we're explicitly saying that this machine is meant to run Python. Here's the explicit path that it needs to run. Here's the hash of the executable that we want it to run, and the destination address and the port. All this information allows us to essentially roll back up to create this full view of the security scope.
Yeah, and it's, just to reiterate something that Chris said, if any of you were at the sessions this morning where we talked about things like security insight, right, the Archon technology piece, that's giving you a runtime state view of things, which is great. It's actually very critical to understand the runtime state. This is providing, as Chris said, this is the provision time state. This is about the intended state of the application components on those. That's really critical because that provides us authoritative context. For all the security guys out there, this is authoritative context that we grab and protect before the machine ever loads, right? And so that gives us a protected thing to be able to look against. All right, so let's take a look at how we apply policy to it.
Right, so this is now where we get into some of the more granular inspection and granular control. So what we're going to be looking at here are the compute security rules on the left. We'll focus on the data security rules a little bit later. And what we have is we've bucketed those rules really into three major chunks. The first is around protecting the operating system kernel. So we can evaluate the state of the kernel, look at every bit of memory in the kernel, and make sure that nobody's manipulating that. Monitoring our host integrity agents. So this is the virtual enclave that Tom described earlier. So this is essentially saying if anyone tries to manipulate our protection mechanisms for the things that we're watching, place a rule on that and notify us when that happens. And then the other three on the top here are more user-space behavior. So when processes start up on the endpoint, when we try to make inbound and outbound connections from that machine, how can we get notification whether those things are proper based on the manifest description? So I'm going to drag in the outbound connections rule. And because of the fact that we have this fully described manifest and that it has created this security scope, we actually don't have to have a very complex rule system here. The rule only really needs to describe what action we want to take when we see a violation, and then whether we want that enforcement to be automated, meaning do it, don't ask me, or manual, ask the security operations team before you make the change. And a key thing, as Tom mentioned earlier, the actions tie into that remediation bucket on the right. So when you look at what potential actions you can take in the system, they're all things that can be manipulated through the software-defined data center systems, right? So you can quarantine a machine via the NSX distributed firewall, shut off all inbound and outbound connections. You can harden the machine, which we expect to be a very common workflow, which is about adding new security services on the fly or changing security policy. You can suspend it using ESX altogether. You can encrypt on demand, and we'll show you the encryption of data in flight in a second. You can run in audit mode, just get alerts. In this case, we're going to block traffic explicitly from our protected agent on the endpoint, and we're going to send an alert to the system. So the next thing I'm going to layer in is the host integrity monitoring. This, again, is what's watching our virtual enclave. In this case, this would be indicative of a very serious threat, so I want to quarantine the machine completely if I see something like this. And I want to do it, though, this time in a manual sense. I want to do it only when the security operations team has said, yes, this is okay.
All right,
I'm going to apply that.
So Chris is now going to push those policies down. Those policies are now going to flow from the management plane out to the hypervisors and into those attestation services that we've built inside the hypervisor kernel, okay? Now,
So what you're looking at here is the host log. So this is the hypervisor log of where the application server is running. And essentially what we're doing is we're going to wait for the rules to get pushed down to the system.
Now, a key thing here, the users of this. Like, as you notice, it's a very different thing, for example, in a firewall where you're essentially defining intended state, right? In this, what we're defining is reaction state. What happens if things doesn't go awry, right? This is where the design point on this is for the security architects to be able to say, these are the scopes that matter from a risk perspective, and here's what I need to be able to either do or recommend to the SOC to be able to do in the event that this starts deviating substantially from the manifest. New things are kicking up. The operating system kernel is being manipulated, for example. And the response pieces that Chris talked about, those we see being used by the SOC team. It's now providing the SOCs not just with alerts, but with easy buttons of here's a set of logical routines to go through, incident response routines that can now be automated, and even with their manual intervention on it, right? That's the concept here.
Okay, so we see that our rules have been applied. This is our little blue highlight here. I learned that trick a few hours ago, actually. So now that the rules are applied, essentially what I can do is rerun the attack, right? So I want to come back to our Kali box.
So now those machines are monitoring against the manifest. Now,
so being that we already dropped our malicious payload on the machine already, what I'm going to do here is I'm just going to execute our malicious payload, just like we did before.
Okay.
Only this time when you come into the host log, what you'll start to see is a bunch of outbound connection alerts. So this is the hypervisor, our monitoring mechanism, notifying you and notifying our management console that we're seeing violations from the manifest. You're putting a connection over a port that's open via the firewall, only you're doing it from PowerShell, which is not what's described in the security scope manifest.
Right.
So we come back to our manager, and now we see that we have an alert, right? Our application server is now under alert. And essentially what this is a notification that you have an outbound connection violation. We've seen unauthorized behavior coming from that endpoint. And in this case, we've already blocked the connection on your behalf based on the policy that you set up before, and we've alerted you. And it's important to note that in this case, you might get to a situation where you need to add this kind of behavior to the manifest, right? So what we're seeing more and more is, developers, infrastructure admins, having the ability to make changes very quickly and without security teams staying up to date. So we feel a lot of the use cases in the system could be monitoring the behavior of the apps and the infrastructure, and then being able to see when new things arise, even if it's not malicious behavior, but adding it to your intended state view of the world right here from this system. In this case, this was malicious behavior, so we're going to go ahead and clear out the alert.
All right. Now, at this point, as an attacker, I'm getting pissed off. Something is blocking and interfering, and the logical next thing to do is to go after whatever is monitoring me or whatever seems to be blocking me. I go after the control itself. So I start to look around, and there seems to be some processes that are monitoring me. So the next attack is to shut down that, to manipulate that. The problem is that for the attacker, the problem is that from the hypervisor kernel, we are doing this from an enclave, and we're looking at that. We're actually freezing those memory pages around that process. We can see a single bit gets manipulated or changed in that monitoring element that we have. This thing, you can't do that without us knowing, right?
Yeah, so what I did is I just, to save time, came right into the app server console, and I ran a little script to manipulate the memory, and you can see in the background here, we get these immediate notifications. All I did was manipulate some code pages and some data pages in our Goldilocks agent, and we get these immediate notifications in real time that we have some page access violations. Coming back to our console, refreshing here, we can see that we have now critical alerts happening on the application server. And in this case, because of the rules that we set up previously, you actually wanted to quarantine the machine if you saw anything violating your host integrity module. So, as Tom mentioned, a very simple way to just confirm and basically manipulate the NSX distributed firewall, and now the machine is immediately in quarantine state. So, just to validate that it is, we'll ping Google.
All right, so Chris is now going to ping. We've just actually reconfigured through NSX to quarantine this. By the way, to the engineers, we have a bunch of the engineers that worked on this in the audience. Guys, this is incredible that you have this up and running. This is all live, everybody, that we're doing this on. So thank you to that.
All right, so we failed. So unless Google's down and the whole world's ending, the quarantine was successful.
Perfect. All right, great. All right. That's the concept of least privilege, and it's a taste of concept of being able to least privilege. By the way, that would be a very different task to try to do that on end-user machines, but for very purpose-built machines on our critical applications in the data center, actually this is very, very conceivable to do with this kind of visibility. All right. But there is no silver bullet in security. If this is to work, it's not only going to lower the attack surface, it's going to create a brighter signal for our behavioral analytics, for the other pieces. And for that, I want to bring up Mike Davis. Mike is the Chief Technology Officer of Counterattack. Mike, welcome. Thank you for joining us. Counterattack is a very interesting company. It's in the endpoint detection and response place, doing a lot of things in behavioral analytics on endpoints. Some very, really interesting stuff, very compelling stuff. And what we wanted to show you is the concept of how these things start to work together and how this can create a brighter signal and remediation options for the kinds of technology that Mike is building. Right? So for that, I think, Chris, you're going to start and actually go back and we're going to actually execute a SQL injection attack. Now, while he's doing this, Mike, explain briefly what a SQL injection attack is.
So a SQL injection attack is a type of attack where a developer hasn't properly sanitized input. So it gives the attacker the capability to control what the database server actually executes. So instead of the attacker getting back normal, say, for example, the name of you as the mortgage holder, they'll potentially get back text about the system or command output.
All right. And the reason we're demonstrating this here is that actually wouldn't necessarily get picked up by comparing to a manifest because we're using the application itself.
Correct. The application is authenticated. It's supposed to be talking to the database, and it's supposed to be executing commands. But we don't want it to execute malicious commands. We only want the proper commands.
So in this case, because we are opening up the context, the manifest to you, how does that help you?
Oh, great thing. So as Tom mentioned earlier, authoritative context is very important. So in a behavioral system like ours, either supervised or unsupervised, the biggest risk is false positives, you mentioned before. You get too much noise. So with the authoritative context that we get from NSX, we're able to reduce the amount of data we have to analyze in real time, and then also provide much more detail on our algorithms on what is good and what is bad.
So because you know the intended state, the intended behavior of that system, you can hone in and provide very deep analytics knowing that that's what you're trying to compare against.
Exactly, without an end user like yourselves having to go in and pre-populate everything.
All right. So, Chris, do we have the SQL injection attack?
Yeah, so I ran the first attack, and what the first attack did was actually tell the SQL Server database to spin off a new process and then dump some system information to a file. And then I just ran a second attack which said, read me that system information and print it out to the screen. And you can see this is all the system information about that database.
All right. So, Chris, let's take a look at the counterattack system that now has access to this piece, and walk us through what we're looking at on these
So
screens,
this is our dashboard.
Those
yeah, you can see a trace here, which is a malicious activity that we've identified behaviorally.
Yep.
And so as Chris drives in here a little bit, you'll see the commands that were actually executed by the database system to retrieve that information that was displayed in the mortgage app.
So what kind of behavior might this sort of pick up on?
This could be anything from interactive command shells. It could be, other connection attempts. It could be accessing other databases on that system.
And then you're scoring it for how weird a behavior this is for given that that's that kind of a system.
Exactly. And the context that we used earlier allows us to actually make the scoring more effective. So we can now know statistically confident that this is malicious than before.
All right. Now, the second part of it is the ability for you now to leverage or recommend the virtual infrastructure to do something about it.
You got it. Yeah, 100%. So remediation, as we saw before, is key to this whole thing. I want to actually do something about this now. Now that we have context of what the attack really was, we can recommend the right type of remediation, one that potentially is going to stop the attack either in a more efficient way or prevent downtime from an actual remediation option.
Great. So let's take a look at our console, Chris.
Right, so we can quarantine directly from here, or we can come into our console. Refresh that, and we see that we have a counterattack issued alert.
Yep.
In this case, they recommended a quarantine action on our behalf, and they're using the same remediation namespace. So you can go through the same remediation actions. In this case, we already showed that, so we'll save time, we'll clear it out.
So the key is, by working together across the industry, we can provide some better context from our position. We can actually watch over whatever agents that are being placed there, so we can watch your back, and you can then leverage it for remediation on the SI.
Yep.
Mike, thank you so much.
Thanks,
That was great.
work. Thanks.
Terrific. All right, Mike Davis, thank you. All right, next, what about containers? Right? The interesting thing about the whole composed service and container world is, actually, this is exactly the direction this is going, right? It's the notion of a manifest is a primary principle behind a container. So this should be a match made in heaven. right? And so for that, we actually worked with an interesting startup called Aqua Security, and we extended the concept here to containers, right? So let's take a look at that.
So we can shoot back up to my screen.
Yes, let's flip over.
What we have is we have a Photon OS image running in Amazon. So Photon OS is the VMware's container operating system. And we have Aqua running on that image. So Aqua has a security agent that they run in the Docker host to essentially give us intelligence about the security scope context happening at the container level, and also providing us with control at the granular container level as opposed to up at the virtual machine level. So what I'm going to do is I'm going to first add 2 containers to our environment. So I'm essentially going to say that I want to add one that's a Redis image, and I want to add another that is a Tomcat 9 image. These are standard images that are pulled from the Docker registry.
Again, these can be multiple containers per VM, right? And it's just that these containers are part of the service that we're delivering here. We want to be able to do the exact same thing we just described, but now on the containers instead of the VM.
So I added just one simple kind of naming convention here just to inform us that the container is part of the VMware Mortgage application. I've lost my view there.
Did you want that screen as well?
That would be helpful, yeah.
All right.
So I'm just going to come into the VMware Mortgage application.
So this is the Aqua
This is
screen.
the Aqua console.
This is the Aqua product.
And essentially what this is giving us is a view that you just added in 2 containers. There are bird cage and our bird feed containers. These are the Redis and the Tomcat images that we just added. And because of the fact that containers have a very well understood and defined description, right? Most Docker files will provide you with all the information necessary to build up a manifest. We can have kind of a preset understanding of the way that container should behave. We should know what executable should be operating. We should know explicitly what kind of behavior it should exhibit. So Aqua has some built-in profiles here that will look at the Redis profile that essentially describe all of the low-level rules and how that container should behave. In this case, it gives us a full list of the allowed executables that you should be seeing in a Redis image, right? Obviously, Redis server is one of them, but there's a bunch of other potential command line tools that you should be able to run. This information is the type of things that we pull into our manifest description to give us that allowed service list to get down to the low-level details.
All right, so let's switch back. And we got to be mindful of time. Let's switch back. Let's take a look at the scope.
So we're going to refresh here, and we'll see that we now have some additional containers added to our security scope, and we now have a microservices tier, Amazon containers, that are now part of this mortgage application. And they've inherited all of the rules that we previously defined, the outbound connections and the host monitoring integrity. And what we're going to do is we're going to drag the process whitelisting rule. And what that's going to do is it's going to essentially give us 2 things. Number one, it'll start looking at the allowed executable list that Aqua has provided, and it'll enforce that allowed executable list using the Aqua agent running in the container host. And it'll also stop any new containers that don't meet a specific policy score from spinning up on the same host. And we can show both of those cases here. So the first thing I'll do is I'll just try to spin up a row container, an NJIX image. This is, a low or a high CVE score container.
Yep.
And we get an immediate error saying, that this kind of behavior is not allowed and it's been blocked from the Aqua server. So, okay, maybe the attacker says, I'm going to try to execute something explicitly in the containers that are already running. So he tries to go into our birdcage container and just run apt-get, which is a command just to install new packages on a Linux box, and normally that kind of behavior would be perfectly acceptable. In this case, it's blocked because of the rule sets that we previously set up.
All right, so you're getting the central idea. If we flip over, you can see what the sort of shows up in the security management console. Here you can see the alerts that are generated.
Right, so now we have, our alerts coming from the container environment. You can come up, Ashu, and we can just clear those out as we did before.
All right, so you get the central idea here, right? The central idea is let's leverage the application team's knowledge about what the intended state of what that machine is. And then we can essentially create an attestation service from a protected area to monitor at load and runtime of those. And our security architects can design policy that says, for the scopes that matter, what do I want to have happen when things deviate in a material way? It also means that third-party endpoint controls can leverage all 3 of those components. That's the central idea here. Make sense? All right. Can we switch them back to back onto the slides? And I want to work quickly to the next and our last topic, which is we've talked about least privilege from a network connectivity and from a compute stack. Now we're going to talk about from a data level stack. I mean, there's a lot of exploits that can move from more on the data plane or from the underlying infrastructure. And the one we're going to talk about here is the one that was referred to this morning by Guido about distributed network encryption. Here's the central idea. The thing we're trying to protect against, in this case, is the physical underlay. If I compromise a switch, if I compromise something in the physical underlay, I'm in a position to listen and see all the internal data of that application as it moves across that component. It's not only that, I have the ability to spoof machines and to be able to manipulate other machines based on that position, right? And that's the central idea here. And if I try to solve this traditionally, I'd have to set up point-to-point encryption tunnels for every conceivable communication pair in this environment. I'd have to manage all the keys associated with that. And I'd have to deal with all the network security controls that no longer have visibility to be able to do deep packet inspection, right? It's a nightmare. It's one of the reasons we don't do a lot of this, right? In fact, a lot of this is tried to address at application level of encryption, which has its own complexities associated with it. Instead, what we do here is deliver encryption as a distributed service, much like we have other elements that are done as a distributed service, and it changes the game, the equation, very, very dramatically. So, what are we going to do? What we're going to do is we're going to break into the bank. And we're going to do that using the physical infrastructure instead of coming down through the compute stack. To do that, we've brought up Ashu. Ashu is actually on the dev team, the QE team on our distributed network encryption. And we're going to flip, if we could flip screens over onto the demo station to Ashu's station. All right, so Ashu, walk us through what we have here. What are we taking a look at right now?
So as you said, we have hacked into the underlay, and there is a Wireshark running here. And we can see all the packets which are going through between the app and DB.
Right.
And since this is like, we can run a script to capture these packets, but we are mostly interested in getting the TDS packets, which usually MS SQL uses to send data between the app and the DB.
All right, so very critical. He's compromised a switch. And by compromising a switch using a free tool like Wireshark, he can now see all the packets that traversing those. So let's log in. We'll log back in.
So I would need a little help here. If you can tell me your password.
It's 1,
1,
2,
2,
3,
3.
4.
Wow, that is the most secure password I've seen.
All right. Let's take a look. Here's my mortgage. All right, so now let's go back. We actually just took a look. Your Wireshark should pick up all of that kind of data in those transactions.
That's correct. As I was saying, we are interested in all the TDS packets, and we can see a whole lot of TDS packets here. But basically, we want to see the database structure of this SQL server so that we can craft packet and induce an SQL injection.
All right, so there's a lot of reasons why you'd want to sniff this traffic and to be able to see this. A lot of confidential data. What we're doing here, we're actually right now looking for the structure of the queries going between this so that we can structure in Metasploit, a tool that we can use to craft new packets, to inject commands. And now that we know the credential and the structure of the database, we can manipulate the database from the infrastructure.
As you can see from the selected packet,
Yep.
the database structure is pretty much open here, and we can see the tables and the columns in the database.
All right.
So we'll use this information and the credentials which we took before from our last attack, and I have a script again inside our Metasploit.
All right, so those of you not familiar, Metasploit, a free tool. It's used a lot in pen testing. It allows us to craft various kinds of attacks, et cetera. We can craft packets on it. So we're essentially running a Metasploit script against the database. What Bashu is doing now is he is creating a machine that is spoofing that Django app server. And it has the credential of it, it knows the structure, and it's sending commands to the database, and the database doesn't realize this is not coming from the actual Django server.
Right, so I've started the pre-created script. It uses the same database structure and the credentials, and it should essentially send an SQL query to the database, believing it, and the database will believe it is the right packet and act on it.
All right.
So if we go back and look at our mortgage app, refresh, and here you go.
Happy days again. All right. Terrific. So we've now gotten rid of the mortgage, this time through the underlay. Okay. Terrific. Chris, let's actually switch the screens over to Chris's screen. We're going to go back to the security management console. And we're going to take a look. Now, some of this has now been built. The encryption in this prototype, we've been building the encryption into NSX. And in this case, we're looking at it through this console. Chris, walk us through what we have here.
Yeah, so we're going to come back into our mortgage app, and this time we're going to be concerned about the data security rules. And I'm going to drag in our encrypt network data rule, and I'm going to use just the default system key and the default key algorithm strength. And I'll apply that.
All right, what just happened when Chris did that is that we've pushed these policies to an encryption filter we've built into the virtual switch. And we've told it that any communication out of any of the machines in this scope needs to be encrypted, authenticated, and integrity checked. And I don't care if those are on a stretched network or on two different sites, this thing all works. It's one key for that microsegment for this scope that is being rotated. All right, so we're pushing that policy down. By the way, on the side, you'll see other types of encryption connecting to other efforts and products inside VMware. If you drag and drop encrypted stored data, it would encrypt all those VMX and VMDK files at rest. If you drag and drop vMotion, that would encrypt. If any of those machines ever vMotioned, they would be encrypted. You can even do network integrity, which is everything but the encryption if you wanted to authenticate and integrity checks. All right, so once we push that policy,
We're good. We'll just go down.
we're going to go over. All right, Ashu, let's see, Mr. Smarty Pants, let's see if you can actually execute this now. What do you see?
Right. So again,
We're going to switch over the monitors onto Ashu. Okay.
again, we are at the same place trying to listen to the traffic. Now we will try to log in and see if we see the TDS packets now.
All right, so we log back
Logged in. I've already resetted the mortgage app.
Okay.
And then if we go back again to our Wireshark and try to run our pre-created filter, yeah, no packets.
There are no packets. Okay, let's take a look at why. Let's show all the...
This is why, because now it is getting all the traffic between app and DB is being encrypted. And if we look at the ESP package, which is IPsec protocol, encapsulated security protocol, we see all the packets are now encrypted.
All right, so if we take a look back at the... all right, you're now blind to it.
Right.
You also, if you tried to execute,
Yeah.
if you actually took the stuff we had before and tried to execute,
Yeah. So we'll try to execute our same script again in the hope that it works.
Yep.
And we'll see that it should fail because now all the packets, as you said, are authenticated and integrity checked.
Right. So here's key. We've just encrypted all of the underlay around this without setting up point-to-point encryption tunnels. This will move when it moves, right? It is completely agnostic to the application, right? It's a big, big step forward. And we believe, well, actually, a lot of the use cases are going to be places where people probably would have thought to use application-level encryption, and instead use something like this, completely independent and completely agnostic to that, right? It's a really, really powerful mechanism to be able, on all fully aligned to everything else.
Yeah.
So it's failed?
Yeah, it has
All
failed.
right.
We can go back and check our mortgage.
All right, so
confirm.
we go back actually to Chris's, go back to the PowerPoint slide if we could. Go back to my deck if we could, and we'll just wrap this up. All right, Guido, in his keynote this morning, talked about extending NSX to the public cloud. Pretty cool. And that movement is also going to enable us to extend these concepts, right? So that if you had virtual machines up in the public cloud, the ability to apply network encryption, as Guido showed this morning, and essentially whether it's a group of machines forming an application in the public cloud or an application that spans, for example, web servers in Amazon connecting to a bunch of things on side, that can be a single microsegment, and you can encrypt that, right? Really, really powerful stuff. And then ultimately, what happens is you have a series of machines, some of which on-prem, some of which are in Amazon, and you're simply dragging and dropping encryption onto that. It's a really, really powerful mechanism. Really, really, I think, really game-changing from a security perspective and how we think about this. All right. Terrific. Chris, Ashu, thank you so much. Really appreciate it. Pretty impressive stuff. That was a live demo, a live hack. 86 million things could have gone wrong on that. It's actually shocking me. All right, so again, the concept here, to be able to think about things in terms of applications, regulatory scopes, to create least privilege and lower the attack surface and create brighter signals based on that and align security controls to it. When we do network least privilege with what we're doing today in micro-segmentation, we're inhibiting all this lateral movement issues that we're contending with, right? Because it's much harder to move laterally into ultimately a separate network or an isolated zone. And we're giving ourselves a policy primitive to align controls to. With the compute least privilege, now we're addressing a separate vector, right? We're taking these machines, we're creating an attestation service to be able to monitor that against its manifest, and we're addressing kind of exploits that are coming in through the application and coming down into that compute stack. And as we extend this to the third leg and do data least privilege, to be able to take that same scope and say, I'm going to apply encryption to all and create confidential communications between these components. Now we're addressing a whole range of exploits that deal with sniffing and spoofing these from the physical underlay, all aligned to the same fundamental primitive. That's what's extraordinarily powerful, right? And, of course, to align security controls to the same primitive, to the same concept, to the same abstraction. This is what we mean by not being about securing virtualization, but using virtualization to secure things, right? In summary, it's an architectural gap that we're contending with more than anything, right? We have to start thinking about how we architect security in. Virtualization opens the door for us to be able to align security around what we're ultimately trying to protect, the application, the regulatory scope. And it enables us ultimately to leverage and create least privilege environments. So, we threw a lot at you. That was a pretty substantial, far-ranging demo. There's a lot of things that you can continue to learn here at the show. There are a whole bunch of other, if you're interested in security briefings to have. Tomorrow, there's another briefing by Bruce Davies on a spotlight on networking, which you should see. And after the show, the video of this session will be available for you to take a look at and for other members of your team that we didn't have an opportunity to come to take a look at. And a bunch of us, including some of the developers, are actually going to be standing by here for a little bit afterwards in case you have some questions. If you want to set up some time or exchange some contact information, if you want to have some conversations with us, because it's really an opportunity to shape the future here. Thank you so much. Enjoy the rest of the show.